Hello everyone, this is Shomita Gupta Roy and this is your channel Physics with Shomita, and today we are going to do photoelectric effect. In this lecture of photoelectric effect, we will cover till work function and kinetic energy of photoelectrons and their relation. And in the next lecture of photoelectric effect, we will be doing the stopping potential and photoelectric current. So photoelectric effect gives us the particle nature of light. It was in 1675 when Sir Isaac Newton first gave the corpuscular nature of light, that light consists of particles called corpuscles. In 1678, Christian Huygens established the wave theory of light. Though at that time, because of stature of Sir Isaac Newton, the wave theory of light was not taken, and corpuscular theory of light remained predominant until in 1881 when Augustin Fresnel could explain the rectilinear propagation of light and diffraction effect of light with the wave theory, and in 1887 when Maxwell established his equation of electromagnetism, and Heinrich Hertz with his generation and of electromagnetic waves, experiments on generation and detection of electromagnetic waves strongly established the wave nature of light. But then in 1905, Einstein with his photoelectric effect established again the particle nature of light. So light today by physicists has two nature, that is wave nature, which explains phenomena like interference, diffraction, polarization, and particle nature, which explains phenomena like photoelectric effect, Compton effect. Okay, so what is this photoelectric effect? Now, if you have a metal, we know metal consists of free electrons, which are responsible for their conductivity, for the conductivity of the metal. Okay. So on this free electrons, if light of suitable frequency, light of suitable frequency, if light of suitable frequency is incident on the metal surface, then these free electrons are ejected from the surface of the metal. This phenomena is called photoelectric effect, and the electrons generated or ejected by the photons by the light are called photoelectrons. We will come to the term photon. So if light of suitable frequency is incident on a metal surface, then electrons are ejected from the surface of the metal. So this emission of electrons from this metal surface under the effect of light of suitable frequency is called photoelectric effect or photoelectric emission. Okay. Now, below a certain frequency, if light of wavelength or light of frequency below a certain frequency is incident on the metal surface, then electrons will not get emitted from the metal surface. It is seen that light of higher frequency or shorter wavelength is more effective. So light of high frequency and short wavelength is more effective. Now, what do you mean by the term quanta? It means discrete physical quantity. Photon is a light quantum. Okay, it is small packets of definite amount of energy. Photon are small packets of definite amount of energy. Now we are going to summarize the photon picture of radiation, of electromagnetic radiation, or photon picture of light. Okay, there are certain important points. Let us see what is the first important point, that in interaction of radiation with matter, photon light behaves as it is made up of particles called photons. Light is made up of, in interaction of radiation with matter, when light is interacting with matter, just as I have shown you that when light is falling on a metal surface, so light is interacting with matter. In that case, light behaves as if it is made up of particles called photons. Okay, So light is made up of particles called photons. Also called light quanta or small packets of discrete amount of energy. The second point is that the rest mass of a photon is zero. The rest mass of a photon is zero. But what does it mean, the rest mass of a photon is zero? It means that photons or light photons cannot be at rest. A photon cannot be at rest. The rest mass of a photon is zero. That doesn't mean that its kinetic energy is zero. Its kinetic energy is not zero. Photons of all wavelength, the third point is photons of all wavelengths and frequencies, whatever be the wavelength and frequency of that photon may be, travel with the speed of light. What is the speed of light? That is c, that is 3 into 10 to the power 8 meter per second. So photons of all wavelengths and frequencies travel with the speed of light, that is with c. Okay, which means of all wavelengths and frequencies, which means whatever the speed of gamma ray, the same will be the speed of X-rays, the same will be the speed of ultraviolet rays. Of course, when the medium is air or vacuum, speed of light in air or vacuum. Because light travels with different speed in different medium. So in air or vacuum, photons of all wavelengths or frequencies travel with the speed of light. Okay, maybe it is a photon of gamma ray, photon of X-ray, photon of ultraviolet rays, photon of red light, visible light. Okay, fourth point is the energy of a photon is given by h nu, when nu is the frequency of the photon. Okay, so there is a relation between energy of a photon and the momentum of a photon. So let us find out that relation in this number 4. Energy of a photon is h nu and rest mass of a photon is 0. But that doesn't mean the dynamic mass or the kinetic mass of a photon is 0. There is a kinetic mass of the photon, which means that when the photon is always in motion, it is never at rest, first of all. And when the photon is in motion, it has its mass given by Einstein's mass-energy relation, E equal to mc square, where E is the energy of a photon and that is given by h nu. Energy of a photon is given by h nu, when nu is the frequency of the photon. Okay, so m is given by h nu by c square. This is the kinetic mass or dynamic mass of a photon. Kinetic mass of a photon. So momentum of a photon is mass, kinetic mass of course, kinetic mass into velocity of the photon or speed of the photon. Kinetic mass is h nu by c square into velocity of the photon is c. So you are getting momentum h nu by c. Okay, now what is the relation between frequency and wavelength? We know c equal to nu lambda. speed of light is equal to frequency of the light into wavelength. So nu equal to c by lambda. Okay, c being a constant. Nu and lambda are inversely related. Nu and lambda are inversely related. More is the frequency, lesser is the wavelength of that photon. Okay, so nu, in the place of nu, I can write h by c into c by lambda. That is, ultimately you are getting h by lambda. That is the expression of momentum of a photon. So what is the relation between energy and momentum? If you are asked to find the relation between energy and momentum, energy is h nu and momentum is h nu by c. So E equal to h nu and P equal to h nu by c. So what is the relation between E and P? In the place of h nu, can I write E? So E by C. So E equal to P into C. This is the relation. E equal to h nu and P equal to h nu by C. So in the place of h nu, I am writing E. So E by C. So E equal to P into C. So this is the relation between energy and momentum of a photon. Okay. So now moving on to the next point, and that is a very important point, that is point number 5, that all photons of same frequency and same wavelength will have the same energy. All photons of same frequency and same wavelength same frequency nu and same wavelength lambda will have the same energy. Because energy of a photon is given by h nu or hc by lambda. Okay, you know the relation between nu equal to c by lambda. Frequency is equal to speed of a photon by the wavelength of the photon. Frequency of a photon is speed of the photon by wavelength of the photon. Lambda is the wavelength. So all photons of same frequency, if the frequency of the photon is the same and of the same wavelength, if the frequency is the same, the wavelength will also be the same, will have the same energy. Okay, the photons will have the same energy. Okay, now if you increase the intensity of radiation, if the intensity of radiation is increased, then what will increase? The number of intensity. On increasing the intensity, the number of photons striking a surface per second increases. So the number of photons per second striking a surface increases on increasing the intensity, but the energy of each photon will remain the same. The energy of each photon will remain the same. Okay, suppose you are having, I want to give the example with photoelectric effect itself. You know what is photoelectric effect, just the basic idea you have, that electrons, these are the electrons in the metal, and on the incidence of light of suitable frequency, electrons are emitted from the surface of the metal. That is photoelectric effect. Electrons are pulled out from the surface of the metal. When light of suitable frequency is incident, each photon will pull out each electron. That is what Einstein has told, that each photon is responsible for pulling out each electron from the surface of a metal. Okay, so suppose one photon is striking here and is pulling out one electron. Okay, and its own existence of the photon is destroyed, and it is giving all of its energy to the electron to pull the electron out of the metal. Okay, so the electron is coming out of the metal surface with the energy of this incident photon. Of course, a part of the energy is required to pull out the electron and rest part is given as kinetic energy to the electron. We will come to that, but for the time being, you assume that this photon is striking the electron and the electron is coming out with a certain kinetic energy. Now, what I am trying here to tell you that if this photon is of yellow light, say you are having a yellow bulb, okay, and this photon is of yellow light of power say 40 watt, then it is 40 watt power, then it is giving out electron, and this electron is coming out with a certain kinetic energy. The electron is coming out from the metal surface with a certain kinetic energy. If you increase the power of the bulb to 100 watt, what will increase? The power of the bulb has increased, the intensity, the brightness of the bulb has increased. What do you mean by increase in brightness? That is number of photons. Intensity increasing means number of photons striking this electron per second, striking the metal surface per second has increased. So the number of photons are increased. Instead of 1, now 3 photons are striking the metal surface. So 3 electrons now are getting ejected from the metal surface. But what about the kinetic energy with which these electrons are getting emitted? That will remain the same. The kinetic energy with which the electrons are getting emitted will remain the same because the energy of the photons have not changed. Only you have increased the power, means you have increased the brightness, means you have increased the intensity. The light has become more intense, means the number of photons have increased. But the energy of each photon is still the same. So the electrons are coming out of the metal surface with the same kinetic energy. Now, if you take the same metal with the electrons, and once you use yellow light, okay, of 40 watt power, so it is emitting 1 electron say, and another time you are using blue light, okay, blue light of 40 watt power, it is again emitting 1 electron. The power is the same. Suppose 1 photon is striking 1 electron and 1 electron is getting ejected. This time what I have changed yellow light with blue light. Wavelength of blue light is less. Wavelength less means frequency is more. Frequency is more means energy is more. So energy of blue light is more. So the photon of blue light will strike this electron with a greater amount of energy, and the electron will come out with a greater amount of energy, of kinetic energy from the metal surface. So here the kinetic energy of the electron has increased because you have changed the wavelength of the light. Because the wavelength of the light has changed. Here it is yellow light, here it is blue light. Though their intensity is the same, but here the electron is coming out with greater amount of energy. Because the energy of the incident photon has changed. The energy of the incident photon is now greater for blue light. For blue light, wavelength is less than yellow. So wavelength is less means frequency is more. Frequency is more means energy is more. So the energy of the photon is more, the kinetic energy with which the electrons will be emitted will be more. Okay. Now this is equation, this is number 5, and then number 6 is all photons are electrically neutral. So photons are electrically neutral and are not deflected by electric or magnetic field. Okay. The seventh point is in photon particle interaction, when photon is interacting with particle like electron, when photon is interacting with electron and photon electron interaction, the total energy of the system remains conserved and total momentum of the system remains conserved. In photon-electron interaction, the total energy of the system. What do you mean by total energy? The initial energy of the system. System means photon and electron both. The initial energy of the photon and electron is equal to the final energy of the photon and electron. The initial momentum of the photon and electron is equal to the final momentum of the photon and electron. But that doesn't mean the number of photons or the before and after collision will remain the same. That is not the case. Number of photons will change, but the energy of the system before collision will be equal to the energy of the system after collision, or momentum of the system before collision will be equal to the is equal to the momentum of the system after collision. Now coming to work function, coming to the term work function of a metal. Work function, what it is? Now we know that metal consists of free electrons which are responsible for the conductivity of the metal. Metal consists of free electrons which are responsible for the conductivity of the metal. Now if these electrons are free, why cannot these electrons escape the metal surface? Because whenever an electron tries to escape, tries to come out of the metal surface, it is held back or pulled back by the positive ions in the metal. These electrons are free because they have left the atoms, turning the atoms into positive ions. So whenever these electrons tries to escape, they are pulled back by the positive ions in the metal. Okay, now so these electrons are bound to the metal with a certain binding energy, and an equal amount of energy or an energy greater than the binding energy is required to eject the electron from the surface of the metal or to pull out the electron from the surface of the metal. So that minimum amount of energy required to pull out an electron from the surface of the metal is called work function of the metal. So what is work function? Minimum amount of energy required to pull an electron from the surface of a metal is the work function of the metal. It is the characteristic of the metal. Work function of a metal is the characteristic of the metal. It depends upon the properties of the metal. Properties of the metal and nature of the surface. Okay, now work function, it is different for different metals. Work function is different for different metals. Like work function of cesium is lowest 1.8 eV for cesium, and for platinum it is highest 5.65 eV. So what do you mean by the statement that work function of cesium is 1.8 eV? What do you mean by this statement? That is, the minimum amount of energy required to pull out an electron from the metals, from cesium metal, is 1.8 eV. Minimum amount of energy required to pull out electron from cesium metal is 1.8 eV. That is the meaning of the statement. A work function of cesium is 1.8 eV. Now, work function, that is the electron can be pulled out from a metal surface by supplying a certain amount of energy to the metal by three processes. First is thermionic emission. What it is? That by suitably heating the metal, certain amount of energy is generated. That by suitably heating the metal, certain amount of energy is generated. That by suitably heating the metal, certain amount of energy is generated. That by suitably heating the metal, certain amount of energy is generated. That by suitably heating the metal, certain amount of energy is generated. That by suitably heating the metal, certain amount of energy is generated. That by suitably heating the metal, certain amount of energy is generated. That by suitably heating the metal, certain amount of energy is generated. That by suitably heating the metal, certain amount of energy is generated. That by suitably heating the metal, certain amount of energy is generated. That by suitably heating the metal, certain amount of energy is generated. That by suitably heating the metal, certain amount of energy is generated. That by suitably heating the metal, certain amount of energy is generated. That by suitably heating the metal, certain amount of energy is generated. That by suitably he thermal energy can be imparted to the sufficient thermal energy can be imparted to the electrons to eject the electrons from the metal surface. So this is by suitably heating. By suitably heating, certain thermal energy can be imparted to the electrons to eject the electrons from the metal surface. Second is field emission. What is field emission? Field emission means by applying a very high or strong electric field of the order of 10 to the power 8 volt per meter. Okay, by applying a very strong electric field, electrons can be pulled out of the metal surface. And third is photoelectric emission. Photoelectric emission, we know when light of suitable frequency is incident on a metal surface, then electrons are ejected from the metal surface. Okay, these electrons are called photoelectrons, and the phenomena is photoelectric emission. Okay, this photon generated electrons, the photons are generating these electrons or ejecting these electrons are photoelectrons, and the phenomena is photoelectric emission. Okay, now we are going to study about photoelectric emission, and we are going to find out the expression of work function with Einstein's photoelectric emission. So explanation of Einstein's photoelectric emission. Explanation of Einstein's photoelectric emission. So in 1905, Einstein explained photoelectric emission with Planck's quantum theory. That radiation exists only in small packets of energy, small packets of definite amount of energy called light quanta or photons. Okay, so with Planck's quantum theory, and radiation exists in small packets of energy, and energy is quantized, and energy can only be like h nu or 2h nu or 3h nu, like this. Okay, energy of a photon is quantized, can be h nu or multiples of h nu. So with this Planck's quantum theory, 1905, Einstein explained the photoelectric emission. So what did he say? That when a photon is striking a metal surface, or it is striking an electron, when a photon is striking an electron, see, one single photon is responsible for the ejection of one single electron. Okay, that is what Einstein has proposed, that one single photon is responsible for the ejection of one single electron. So when a photon is striking an electron, okay, it is giving whole of its energy to the electron. How much is the energy of a photon? H nu. So whole of the energy of the photon is given to the electron. This is the photon, say it is a particle, and whole of its energy is given to the electron. And the electron is getting emitted. Now, this electron which is getting emitted has a certain kinetic energy, and how this energy of the photon is getting divided. This energy of the photon is used up in ejecting the electron from the metal surface. In ejecting the electron from the metal surface and imparting a certain kinetic energy to the electron. So this electron, this photon, energy of the photon is used up first in ejecting the electron from the metal surface. That is in providing work function to the metal. Work function of the metal, this meeting of the work function of the metal. In ejecting the electron from the metal surface and in imparting kinetic energy to the electron. Now if the electron, all electrons are not on the surface of the metal, some are within the metal, okay. Now whatever energy this electron will come out with, this not with the same kinetic energy this electron will come out with. This electron will come out with a lesser kinetic energy because it will undergo more collisions. Try to understand. When an electron is within the metal, it will undergo more number of collisions before coming out of the metal surface. So the electrons which are within the metal will not come out with the same kinetic energy as the electron which are present on the surface of the metal. Okay, so Einstein gave the equation for the electrons which are on the surface of the metal, that the energy of the photon is used up in giving maximum kinetic energy to the electrons plus in ejecting the electrons from the surface of the metal. So it is used up in H nu is used up in providing maximum kinetic energy to the electrons and in ejecting the electron from the surface of the metal. Okay, now let us do it again. H nu is equal to K max plus W, where W is the work function of the metal. You can use W or you can use phi naught, anything. Work function of metal. W is the work function of metal. So the total amount of energy of a photon is used up in ejecting the electron from the surface of the metal plus providing kinetic energy to the metal. To the electron, ejecting the electron from the metal surface plus providing maximum kinetic energy to the metal surface. Now, not all electrons are coming out with the same kinetic energy. We can show you, this is the energy of the photon, this is the work function of the metal, these are the collisions, and this is the kinetic energy with which it is coming. Suppose the energy of a photon is 10 eV. This is in eV, this is in eV, this is collision, and this is in eV. Okay, eV, 1 electron volt. Okay, that is the unit in which work function is measured. 1 electron volt is equal to 1.602 into 10 to the power minus 19 joule. Work function of a metal is always measured in electron volt. You are going to find out the answers in electron volt. So work function of a metal is 1 eV is 1.602 into 10 to the power minus 19 joule. 1 eV is the energy acquired by an electron when it is accelerated under a potential difference of 1 volt. Okay, energy acquired by an electron when it is accelerated under a potential difference of 1 volt. Now, energy of a photon, if it is 10 electron volt, okay, and work function of a metal is 2 electron volt. Okay, so a photon, these are the electrons. A photon of 10 electron volt energy is incident on the metal surface, and the work function of the metal is 2 electron volt. And electron is ejected from the surface of the metal, so it is ejected with maximum kinetic energy. It is not undergoing any collision, so the number of collision is 0, and the kinetic energy is 8. So 8 plus 2 is equal to 10. 2 plus 8 is equal to 10. But if the energy of the photon is 2 and the work function of 10 and work function is 2, and the electron is undergoing 2 collisions with 2 other electrons, or with positive ions, then the kinetic energy with which it will be emitted will be 6. 6 plus 2 plus 2, that is 10. So here the electron is not getting emitted with maximum kinetic energy, just like this electron which is emitted with maximum kinetic energy. Okay, this electron is emitted with maximum kinetic energy. Here the electron is not getting emitted with maximum kinetic energy. Understood? So maximum kinetic energy, the electron is emitted with maximum kinetic energy when the electron lies on the surface of the metal and it does not undergo any collision with any other electron or positive ion. Okay, then only the electron can get emitted with maximum kinetic energy, and this is Einstein's photoelectric equation. Now we are going to find out the expression of this W, work function. Okay, now electron, try to understand, h nu, the energy of the photon should be greater than the work function of the metal. Work function means the minimum amount of energy required to eject the electron from the metal surface. So the energy of the photon, I'm again drawing the diagram. This is the photons of suitable frequencies of energy, suitable energy. This energy of the photon should be greater than the work function. The work function of the metal is 2 eV. Then 2 eV amount of energy is required to eject an electron from the metal surface. If the work function of the metal is 2 eV, then 2 eV or greater than that energy is required to eject an electron from the metal surface. That is the meaning of work function. So the energy of the photon should be greater than or equal to the work function of the metal for photoelectric emission to take place. Energy of the photon should be greater than or equal to the work function for photoelectric emission to take place. Okay, or nu should be greater than equal to W by H, or nu mean is equal to W by H, and if we take this to be nu naught, then W is equal to H nu naught. This is the expression of work function. The energy of the incident photon should be greater than or equal to W. It can be 2 electron volt, or you may understand it in this way, that if the energy of the incident photon is equal to the work function of the metal, if this energy of the incident photon is equal to 2 eV, then the electron will come out of the metal surface with zero kinetic energy. Isn't it? If this h nu becomes 2 and the work function of the metal is also 2, and it is from the surface of the metal the electrons is undergoing zero collision, then it will come out with zero kinetic energy. But it will come out. Okay, but it will come out because it has met the condition of work function, minimum energy required to eject an electron. But it will come out with zero kinetic energy. So you can put here h nu, when the energy of the incident photon is equal to the work function of a metal, then the electron will come out with zero kinetic energy. So if you put here this expression h nu equal to 0 plus W, this minimum amount of energy has a minimum frequency nu naught. So h nu naught is equal to W. This minimum amount of energy has a minimum frequency nu naught. H nu naught is equal to W. Okay, this minimum frequency of light is called the threshold frequency of the metal. Threshold frequency of the metal. Okay, what does it mean, threshold frequency? The minimum frequency of the incident radiation required to eject or pull out an electron from the metal surface. Minimum frequency of, I'll write down, minimum frequency of incident photon required to eject an electron from metal surface, or minimum frequency of incident radiation required for photoelectric emission. Minimum frequency, it is threshold frequency of metal. It is different for different metals. Different for different metals. It is also characteristic of the metal. Okay, threshold frequency is also characteristic of a metal. It is different for different metals. Okay, it is minimum frequency of incident photon required to eject an electron from metal surface. Now, if threshold frequency is nu naught, what will be threshold wavelength? What will be threshold wavelength? Let us see. H nu naught is the walk function. Okay, when nu naught is the threshold frequency, so threshold wavelength will be C by lambda naught. Lambda naught is the threshold wavelength. What it is? It is inverse of threshold frequency. So it is the maximum value of incident, maximum wavelength of incident radiation above which there is no photoelectric emission. This is the maximum wavelength of incident radiation above which there is no photoelectric emission. Maximum wavelength of incident radiation above which there is no photoelectric emission. This is the threshold wavelength. Now, walk function, as I have told you, walk function is the minimum energy required for photoelectric emission. If the energy of the incident radiation is equal to the walk function, then the electrons will come out with zero kinetic energy. So you may define walk function as the minimum energy required to eject electron from the metal surface with zero kinetic energy or with no kinetic energy. Okay? Minimum energy required to eject electron from the metal with surface with zero kinetic energy. Okay, that is the walk function of a metal. Okay. Now, if I have to plot a graph of kinetic energy of the emitted electrons, this is the kinetic energy, K max, and this is the frequency. Okay, so this is the equation. Equation is H nu is equal to K max plus H nu naught. Now W is equal to H nu naught. Okay, so K max is equal to H nu minus H nu naught. This is Einstein's photoelectric equation, or in the place of K max you can write half m V max square equal to H nu minus H nu naught. This is Einstein's photoelectric equation. Okay, when nu naught is the threshold frequency. Now if you have to plot a graph, then this equation, isn't this looks like y equal to mx minus c? So a negative intercept, and it is something like this. Sorry, this will be dotted. This is just extended, and from here it will be a straight line, okay, with a negative intercept. So what is m? M is the slope. Y equal to mx minus c. M is the slope. You are plotting y against x, that is K max against nu. So from the slope you are getting h, okay, K max by nu, you are getting K max by nu. If you plot, you will get h. H is the slope. And what is the intercept? Intercept is c, that is H nu naught, that is the walk function. So this intercept is nothing but the walk function. So questions may come, a graph may be given and you may be given here. I will do the similar question with you, but you may be asked to find out the walk function from the graph, and you have to find it out by seeing the intercept on the negative y-axis. Okay, so this is one, and if you have to, and this, what is this point? This is the point, this is the minimum energy above which there is photoelectric emission, and minimum energy below which there is no photoelectric emission. So this is the threshold frequency. This is the threshold frequency. Okay, This is the minimum amount of energy required, okay, above which there is photoelectric emission. You can see work function above which there is photoelectric emission, and this is the minimum frequency, threshold frequency, minimum frequency of incident radiation above which there is photoelectric emission, okay, above which there is photoelectric emission. Now if you have to plot Kmax is equal to h nu minus h nu naught, I can also write it hc by lambda minus hc by lambda naught, okay, Kmax. And if I have to plot Kmax against 1 by lambda, this is Kmax. You know Kmax, the maximum kinetic energy with which the electrons are coming out of the metal surface, and this is 1 by lambda. Then it is again something like this. Straight line, no bending. Okay, this is 1 by lambda naught. Well, lambda naught is the threshold wavelength. That is the maximum value of the wavelength above which there is no photoelectric emission. If the wavelength of the incident radiation exceeds lambda naught, if wavelength of incident radiation exceeds lambda naught, there is no photoelectric emission. Okay, so this intercept, what is the slope? Again do y equal to mx minus c. M is here, you are hc is m because you are plotting Kmax with 1 by lambda. So from here you are getting hc, and the intercept is hc by lambda naught. It's nothing but the work function. Okay, and this is 1 by lambda naught, where lambda naught is the threshold wavelength. Now suppose you are having two metals A and B with 2 electron volt work function and 4 electron volt work function. Which metal will have lower threshold wavelength? Lower threshold wavelength. Can you tell me? What is work function? H nu naught, that is hc by lambda naught. Now lambda naught is inversely proportional to W. So W is greater for B. So lambda naught will be less for B. So B will have lower threshold wavelength. Okay, W is greater for B, so lambda naught will be less for B. W is inversely proportional to A, lambda naught. Okay, this is one question, and you may have another question. Suppose you are having copper and sodium, and it is difficult to emit electrons photoelectrically from copper than from sodium. Okay, it is difficult to emit photoelectrically electrons from copper than from sodium. So which metal has higher work function and higher threshold wavelength? So if it is difficult to emit electrons photoelectrically from copper, then copper definitely has a higher work function. More energy is required to eject electrons from surface of the copper metal. So copper has a higher work function. If copper has a higher work function, it will have lower threshold wavelength, because work function is inversely proportional to threshold wavelength. So it will have lower threshold wavelength. So copper has higher work function and sodium has higher threshold wavelength. Okay, so these are some of the questions that may come, and we will be doing 2 numericals, and we will end with this. And 2 important points that has to be done is, first is the intensity of the incident radiation. If the intensity of the incident radiation increases, then it will increase the number of photoelectrons coming out of the metal surface. Okay, intensity means the number of photons striking a surface per second. So if the number of photons increases, the number of electrons coming out will increase. So it will increase, if intensity increases, it will increase number of photoelectrons emitted. But it will not increase the energy of the photoelectrons emitted. Kinetic energy of the photoelectrons, not increase the kinetic energy of the photoelectrons emitted. Okay, intensity increase means number of photons striking a surface per second. If that increase, the number of photons is increasing, then one photon ejecting one electron. If 5 photons are there, then 5 electrons will get emitted. Okay, but that will not increase the kinetic energy of the photoelectrons, because kinetic energy of photoelectrons depends upon the energy with which the photons are incident on the metal surface. Okay, and second is the energy of the incident radiation should be greater than the greater or equal to the work function of the metal. If the energy of the incident radiation is less than the work function, greater than or equal to h nu naught. If h nu is less than h nu naught, then what will happen? In this equation, K max plus h nu naught. If h nu is less than h nu naught, that is, this is 1, this is K max, and this is 2. Work function is 2 and the energy of the incident photon is 1. Then K max is becoming negative, you see. K max is becoming minus 1, which is not possible. Kinetic energy cannot be negative. So that is not possible. So photoelectric emission will not take place if energy of the incident photon is less than the work function of the metal, the minimum energy required to eject an electron. Okay. Third is, there is no time lag between the incidence of the photon on the metal surface and the ejection of the electron. There is no time lag between the incidence of the photon and the ejection of electron. And with all this explanation of photoelectric effect, in 1921, Albert Einstein was honored with Nobel Prize. Okay. Now, we are going to do a few numericals. One more thing I want to tell you, that if we perform experiments with two different metals, say with cesium and with platinum, okay, and we plot the graph of Kmax versus frequency, then we will find that both will give a straight line graph. Means that the slope, and they will be parallel to each other. Parallel graphs means their slope will be the same, because slope of Kmax versus nu is h, Planck's constant. Since it is a constant, the slope will come out to be the same. But what will be different will be the work function, the intercepts, the work function. Okay, so the work function for platinum will be more than the work function for cesium. Okay, but the graphs will be straight line. So if you take different metals, you will get straight line graphs which are parallel to each other with the same slope. Okay, because slope will remain the same. Now we will move on to numericals, and the first numerical is, we'll be just doing two numericals because later on I will make another video on numericals for this kinetic energy and nu. We are having a graph. You can see the maximum kinetic energy versus the frequency graph. Okay, frequency into 10 to the power 14 hertz, and this is the maximum kinetic energy. Just look at the graph properly. Now you were asked to find nu naught, the threshold frequency, the minimum frequency of the incident radiation required for photoelectric emission. That is 10, you can see. So the nu naught is equal to 10 into 10 to the power 14. Don't forget to mention 10 to the power 14 hertz, because nu into 10 to the power 14. Okay, what is the work function? Next question is the work function of the metal. Work function is the intercept, this. So work function is 4 electron volt. K max is in electron volt, this axis is in electron volt, so work function is 4 electron volt. Next is h, the Planck's constant. Now h has to be derived. Okay, the Planck's constant we have to derive. So let us derive the Planck's constant. W is equal to H nu naught. So H is equal to W by nu naught. So W is 4 electron volt, 4 electron volt, 1.6 into 10 to the power minus 19, and nu naught is 10 into 10 to the power 14. So how much are you getting? You will get 0.64 into 10 to the power minus 33 joule second, or 6.4 into 10 to the power minus 34 joule second. Okay, that is H. And then we were asked to find K max at 30 into 10 to the power 14 hertz. So at 30 you can see K max is 8. It is clear from the graph, but still you can work it out since you were asked to calculate. So you have to calculate it. It's better to remain in the safe side and calculate. So K max is equal to H nu minus H nu naught, that is W. W we know, what is H we know, and H nu is 30. Nu is 30. So H is 6.4 into 10 to the power minus 34, and nu is 30 into 10 to the power 14 minus H nu naught, that is 4 electron volt into 1.6 into 10 to the power minus 19 electron volt to joule. Okay, so this is H, this is nu at K max at 30 into 10 to the power 14 hertz. At this point, what is K max? So H nu minus this, so it will come out to 19.2 into 10 to the power minus 19 minus 6.4 into 10 to the power minus 19. That is, it will come out to 12.8 into 10 to the power minus 19 joule, which you can change to electron volt by dividing with 1.6 into 10 to the power minus 19. You will get 8 electron volt. That is what it is. Now if you are asked to find threshold wavelength, will you be able to find out threshold wavelength? Threshold frequency, you have nu naught. So nu naught is equal to C by lambda naught. You just have to get lambda naught is equal to C by nu naught. Lambda naught is C by nu naught. C is 3 into 10 to the power 8. Nu naught is 10. Nu naught is 10. 10 into 10 to the power 14, and you will get in meter. Okay, something in meter you will get, that you will multiply with 10 to the power 10 to get in angstrom. Okay, that will give you the lambda naught. You will get something in meter, that you will multiply with 10 to the power 10 to get in angstrom. Now the another question is, the surface of a metal is illuminated with light of 400 nanometer. Kinetic energy of the ejected photoelectrons is 1.68 electron volt. You have to find W. Okay, so surface of a metal, so lambda is given. That is 400 nanometer. Okay, kinetic energy is given. K max, kinetic energy of the photoelectrons is 1.68 eV. That is, K max is given 1.68 eV. Okay, so use Einstein's photoelectric equation, that is K max plus H nu naught. H nu naught you have to find out, W you have to find out. So Hc by lambda is equal to 1.68 plus W. Now Hc has a value of 1240 electron volt nanometer. Okay, so taking this 1240 electron volt nanometer by 400 nanometer is equal to 1.68 plus W. So 0 0 gets cancelled. 4 3s are 12, 4 1s are 4. So 3.1 electron volt minus 1.68 electron volt is equal to W. So W is coming out to be 1.42 electron volt. Okay. Similarly, you may be given the work function and you may be asked to find out the threshold wavelength. Okay, suppose the work function is given, you may have another question. Suppose the work function is given 4 eV and you may be asked to find the threshold wavelength. So how you are going to find out work function? Work function is W, we are denoting it with W. So W is equal to H nu naught is equal to Hc by lambda naught. And Hc has a value of 1240 electron volt nanometer. So 1240 electron volt nanometer by W is equal to lambda naught. By W is 4. So you are getting 310 nanometer. Okay. So this type of questions may come and we'll be doing more questions in our other videos. Thank you.